Yeah. I don't have it on as a video on the web, so I have to changing some of them. Okay. What does it mean for a function to be continuous? In English, it means, can you draw the function graph from left to right without lifting Stuart your It's really all we're going to talk about today. Can you draw the functions graph without lifting your pencil? We're going to talk about that. But okay, I'll put it here. The limit as x approaches a of f of x has to equal f of a for all x's in the domain. They're for all. The upside down a is for all. X is in the function's domain. What it's saying is every single point as you move from left to right. Well, that's a crappy graph. Anyways, as you move from left to right, the limit from the left and the limit from the right have to match, and they have to exist, and there has to be a number, and it also has to match the y value there. Okay? So, but for that to happen mathematically, if you can put your finger on the left-hand side of the graph and trace it over with your pencil without lifting your pencil, the function is continuous. Duh. You know, it's like one of those duh moments. If I don't lift my pencil, it's a continuous, nice, smooth curve. Okay, so find the points where the function is discontinuous. So where is the function not continuous on the graph below? Where? One and discontinuous at x equals 1 and x equals 2. Find the points where the function is continuous. Well, where's the function continuous? It's continuous UOUS on the interval in. So we'd start drawing at 0. We pick our pencil up at 1. We put our pencil down at 1. We draw until we get to 2. We pick our pencil up at 2. We put our pencil back down at 2. And we go all the way to 4. Oh, and square bracket at 4. Sorry. What about the 1? I'm just thinking about that one here. This one might be like this. Equals. Yeah. No. Okay, fine, I'll write it this way. You might like this better. Okay, what is the relationship between the limit of f and the value of f of each point for the... Okay. X is between 0 and 4, but not equal to 1 and 2. Yeah, no, it's equal. It has to be equal at 0 and 4. Yeah. No, I'm being steely. No. No, it's a point of discontinuity. Now we're going to talk. Okay, you're starting to get ahead of yourself because I was just, and I was too. We're going to talk about left-handed continuity and right-handed continuity. You would say the point x equals 1 has right-handed continuity? No, left-handed continuity. Left-handed continuity. Yeah, but you don't need to worry about that. Just relax. Okay. I want everybody to take a look at the point. There's 2 points we want to look at. I want to look at x equals 1. I want to look at the limit as x approaches 1 from the left. I want you to tell me the y value. And the limit as x approaches 1 from the right. Tell me what f of x. As x approaches 1 from the left, you would say it's 0. As x approaches 1 from the right, you would say it's 1. So you would say about the point, the limit as x approaches 1 does not exist yet. Okay, tell me about the point x equals 2. The limit as x approaches 2 from the left, the limit as x approaches 2 from the right, the limit as x approaches 2, and then tell me what f of 2 is. So 2 from the left is 1, 2 from the right is 1, as x approaches 2 is 1, but f of 2 is 2. And that's why we would say it's discontinuous, because these two numbers don't match each other. Got to be the same number. And the reason we say x equals 1 is discontinuous is because the limit, there's no limit, so we can't even start the process. Okay? What about x equals 3? The limit is 2, and the y value is 2. So we're happy. They match. Continuous. Okay? So the first two are discontinuous. The third one is continuous. So 2 non-examples and an example. Cool? Flip the page. What? No, ask. Wait. As x approaches 2 from the left, that's coming in this way. That's 1. As x approaches 2 from the right, you're coming in this way. And your fingers are pointing at the same place. So, okay. Continuity to point. Definition. A function is continuous at an interior point C if the limit as x approaches C of f of x equals f of c. So what we're saying here is I'm going to draw a little picture for you. Draw a little picture for you. So you have some point right here, C. So what we're saying is the limit from the left has to match the limit from the right, and they have to be the same. And that's what this is saying. Has to match the y value at C. So the limit from the left has to match the limit from the right, and it has to be the same. So the limit from f of x, the limit as x approaches C of f of x has to have the same y value at C. That's what we just saw on the previous page. Here's where we get to be a little bit funky. So, endpoint continuity. A function is continuous at the left point, endpoint A, or is continuous at a right endpoint B of the domain if the limit from only one side, so as we slide into A, it has to match the y value at A. And as you slide in from the other side into B, it has to match the y value at B. Right. But both of those points, so that's what I was trying to say when Phil was talking, we were talking about something, I was saying, well, there's left endpoint it's left endpoint continuous, but no. A is left endpoint and B is right endpoint. Left, right? So A and B have endpoint or endpoint continuity, but this one doesn't have left endpoint continuity and B does have right endpoint, right? Right isn't correct. B has right endpoint continuity and A does not have left endpoint continuity. Correct? I know. Okay. Fine print. If a function is not continuous at some point C, what do we say? We say there is a point of discontinuity in the function. Note that C does not need to be in the domain of the function f. Now you're thinking to yourself, huh? Well, okay, let's look at the graph of y equals 1 over x. Tell me what value is not in the domain. But if we graph it, we would say there is a point of discontinuity at x equals 0, even though that 0 isn't in the function's domain. We need to know basically we need to know where the problems are. We need to know that there's a problem at 0. If we're going to try and do some calculus, eventually, chapter 3 and 4 stuff, around the point x equals 0, we need to know that it's going to blow up in our face big time. So we need to know where the points of discontinuity are. Even if it's not in the function's domain, everybody goes, well, who cares? It's not in the domain. It does matter. It still matters. Okay? So the fine print. So find the points of continuity and the points of discontinuity in the greatest integer function. So the greatest integer function is that step function that we drew a couple of days ago. I'll draw it for you. It's easy to talk about the points of discontinuity first. Where's the discontinuity? Points of discontinuity, x equals -1, 0, 1, 2, 3, 4, 5, 6. Who wants to write them all out? Well, you could just say x is an x equals n, where n is an integer. Points of continuity? Well, the points of continuity are any numbers between negative infinity and positive infinity, but not where x is not an integer. Yeah? Are you guys okay with the NEI notation? Okay. An analysis of some of the important types of continuity. Okay. B. A is a continuous function. Continuous function. B. What's that thing at 0 called? A point, what kind of discontinuity? Okay, it can be called a point discontinuity. It can be called a hole. A hole. It also can be called a removable discontinuity. It's easy to fix. A little bit of drywall, you can fix that bad boy real fast. It's a poster. The next one, same thing. You can call it a point discontinuity, you can call it a hole, you can call it removable. Okay. Oh, flip the page. You'll see some. There's lots of different kinds of discontinuity. Okay. D. D is called a jump discontinuity. Jump. Y equals 1 over x squared. In this graph it looks like this. Where are those red arrows taking you off to? Infinite discontinuity. What? Well, you can't stop and think about this. You're going to draw. I'm going to go to Never Never Land. But Mr. Up, I can join those. Oh, really? Okay. I know, but I just want everybody in the room to realize that if you say you can, you're going to say you can draw this to infinity and then you're going to join it up. No. Don't do that. Well, that point, they get closer and closer together, but they're still climbing, right? They're still climbing. They're never going to stop climbing, so there's no linkage there. Okay? Okay, y equals sine of 1 over x. So what I would like you to do is throw this in your graphing calculator, and we're going to look at values around 0. Now, if I had my iPad here and I could hook it up to my projector, the graph on the projector is pretty awesome, but we'll have to suck it up and do it on this. No, it's because I have to. No, it's actually because I have to crack my iPad to work on a projector. Jailbreak it. Yeah. Yeah, I'll get right on that, Spence. So, cool? I just used ones. Now, what I'm going to do, and I don't want you to do this along with me, but what I'm going to do is I'm going to knock those ones down to negative 0.5s just to get a better view of things. And I'm going to knock the 0.5s down to 0.25s to get a better view of things. Oops, you're an idiot, Mr. App. I know I am, but why not graphing it? There we go. Do we agree that we really don't know what's going on around 0? It seems to be going up and down. Earthquake. What? No, it would get worser and worser. We call this an oscillating. It's an oscillating discontinuity. How we doing? Good? An oscillating discontinuity. We have jumps, infinite, oscillatings, and removables. There's 4 kinds of discontinuities. I feel very much like a biology teacher right now. We can classify things now. You are the oscillating discontinuity group. Factor the, okay, sorry, I just offended some biology students in here. Factor the denominator, please. Really? Have I factored it for you? No, it should be x squared minus 9. Oh, what is it? Oh, okay, I made the question easier because I didn't want to waste time. Yay, what was it? Minus 5x. Okay, factor the denominator. Hey, it's done. What is the domain of the function? You can tell me that. X is all real numbers. Sorry. We're going to write it in calculus notation now. X is in the interval negative infinity to positive infinity. X cannot equal 3. X, epsilon. X is an element. Epsilon. Okay, throw that in your graphing calculator. What I want you to do is to trace around the number 3. Well, so we can decide what kind of discontinuity it has by looking at the graph around the value of 3. Bracket. What? Yeah, but I'm pretending that we're not doing that. So just hang on. You're doing something later. No. I'm trying to type the function in my calculator, but I'm doing it very badly right now. There. Good? Okay. Do. Trace around the value x equals 3. Okay, well, we'll do that. Trace. Hey, Mr. App. This calculator is so cool, it skips right past 3. Did you notice that? Yeah? Okay, so do we think we can fix the problem? Yeah, probably, because we can't even see the problem. Calculator can't draw a whole or removable. It doesn't do it. So if you go trace 3, enter, it should say nothing, right? Okay. So we did that. How should x equals 3 be defined to remove the discontinuity? Oh, well, you zoom in and tables is necessary. Oh, okay. Well, let's do that. Cool. Do you see the hole now? There's be a little tiny space in the graph. Anyways, isn't that cool? Anyways, so we trace a little bit to the left, and we say, hey, cool, Mr. App, if we let looks like if x is 3, y could be 1, hey? Does that kind of... When x is 3, if we made y equals 1, that would be a happy thing. Mr. App, I don't like that way of thinking. Maybe if you looked at a table of values. .5, 3.5. hey, Mr. App, if we let when x is 3, y would be 1, that might be a good thing to do. So we've done it graphically, we've done it numerically. Here's how we do it analytically. We do the limit. Okay. So how should we define it? Well, we could use the limit as x approaches 3 of x squared minus 5x plus 6 over x minus 3. Mr. App, factor the numerator. Somebody already started to talk about that, and I shut them down. And it's because I want to do this last. X minus 3, x minus 2 over x minus 3. What happens to the x minus 3's? So you're left with the limit as x approaches 3 of x minus 2. Mr. App, I can substitute the 3 in now. 3 minus 2 is 1. So you can fix the hole, you can fix the removable discontinuity by using a little bit of spackle, little drywall filler. Yeah. Yeah. So we can change the function into x squared minus 5x minus 6 over x minus 3 when x doesn't equal 3, and we change it into y equals 1 when x does equal 3, and it fills the hole in for us. Cool? We fixed the problem. Spence. What? Because what I'm doing, I'm going to draw a picture now. What we just did is if we leave the problem alone, if we leave the function alone, we get a graph that looks like this. Okay? When x is 3, y is 1. But what we do is we add in this one to fix the problem. What are you saying? Yeah? Okay. X squared minus 5x plus 6 over x minus 3. If I graph this function, it looks like this. So we're going to use that red line wherever x isn't 3 because we have a problem at 3. So what we could do is, the other way we could write it is x is in the interval negative infinity to positive infinity, x cannot equal 3. So we're going to use that line when we're everywhere except for 3, and when we're at 3, we're going to use the point 1, because that's going to fill in, we're going to use the point 1 when x is 3, and that's going to fill in our hole. It's going to put the spackle where we want it to be. We're making a piecewise function that makes the function continuous. Because, why? If it isn't continuous, we can't take its derivative. And if we can't take its derivative, we might as well not even worry about calculus. It has to be, calculus only works with continuous functions. So if we have stuff that's discontinuous or points of discontinuity, we would like to fix them before we move on. Okay? It's like doing body work on the car before you sell it.
All you do to fix it is know where it is.
And then fix it if you can. And if you can't fix it, then you have to acknowledge the problem and go, I'm not going to look at that part of the graph. Pardon me? An infinite discontinuity, an oscillating discontinuity, a jump. You just have to acknowledge the existence of those places and you will avoid them like the plague. Yes. Spence. Is 1, yeah. Yeah. Are we good now?
Sure.
You need to think about that a little bit, I think. Okay, keep on going. Here we go. The fine print. Some more fine print. A function is continuous on an interval if and only if it is continuous at every point in the interval. A continuous function is one that is continuous on every point. So we need to notice the difference. There's two different statements here. A continuous on an interval if it's continuous at every point in the interval. A continuous function is one that continuous on every point of its domain. A continuous function need not be continuous on every interval. For example, y equals 1 over x is continuous in its domain, but it is not continuous on the interval -1 to +1. Because at x equals 0, we have a point of discontinuity. Because 0 isn't in its domain. I know, it's kind of weird. Like, no, but those aren't coordinates. Those are. It is continuous. Okay. Let's read that sentence again. A function is continuous on an interval if and only if it is continuous on every point in the interval. A continuous function is one that is continuous in every point of its domain. They are not saying the same thing.
So it says -1, comma, -0.001.
It would be continuous on that interval, yes. So if we flip back to that very first example, we would say that function in this investigating continuity, that picture, we would say that function is not continuous at these points. But if I talked about the interval 3 to 4, you would say it's continuous on that interval. See what I'm... Sure. Or we're only looking at specific parts of the graph. Like, that's how we can get around these problems. We can talk about the jump discontinuity being continuous from -infinity just up to 0, and from just past 0 up to +infinity, because they're continuous on those intervals, but the function isn't continuous, because at 0 we have a problem. So we fix the problem about continuity by going, well, we don't have to be continuous everywhere. As long as we're continuous on a good interval, we're okay as well.
So for every point, we continue, every point has to be continuous,
Except for the endpoints. Yeah? And it just comes down to, can you draw it without lifting your pencil? Just have that in the back of your mind. Okay, is y equal 1 over x is continuous function? Well, we just said it's not continuous on 0, 0. Is it continuous? It's continuous on its domain. Yes. So, is it a continuous function? Yes. Because, good, x equals 0 is not part of its domain. But we still acknowledge and respect the existence of x equals 0, and we call x equals 0 an infinite discontinuity. Okay. The types of discontinuity? Yeah. Okay. Here's where it kind of comes interesting. If you have two functions, and they're continuous when you add them together, they're continuous. If you have two functions and you subtract them, if they're continuous before, they're continuous after. If you multiply them and they're continuous before, they're continuous after. If you multiply them by some number k, they're continuous before, they're continuous after. No. Look at how I say. I'm not saying discontinuity. I'm saying if they're continuous before, they're continuous after. If they're discontinuous before, we probably will have problems after, but they move around. if they're continuous, if f of x is continuous and g of x is continuous and you add them together, the new shape will be continuous.
So this is just for the
Yes. Then, continuous x equals c. But c can be at any point in the function's domain. So I'm really talking about the whole graph. Because every point c, right? Not just a point c, every point c. I'm doing both at the same time, yes. Just wait, okay. Sure. So here's f of x. Here's y equals f of x. That's continuous everywhere. And here's y equals g of x. Okay, are those functions continuous? If you add those two functions together, you get a new shape. Would you agree? Would they be continuous? Yes, they would. We don't even need to worry about it. If no, we're not. So I'll put them. I don't like you guys sometimes. Yeah, you're right. It is Spencer. Okay. Here's me playing with your brain. I don't know if you know that you can do this on your calculator. If we add them together, so y1, y2, if we add them together, is the function continuous? Yes, it is. It's the yeah. No. If we add them, are they continuous? If we subtract them, are they continuous? Yes. If we multiply them by some number 3, are they continuous? Yeah. If we divide them, are they continuous? Yes, as long as you don't divide by 0. As soon as you divide by 0, you could have an infinite discontinuity. You could also have a removable discontinuity. You could also have an oscillating discontinuity. All of those could appear. Okay? So, what is a composite function? It is a function of a function. It is a function of a function, or a function within a function. So an example of that is g of x equals, see if you guys, I'm going to use colors here. Why did I do that? That's stupid. There. I guess I should call that something other than G, H. So what we're talking about is H is F inside of G. Remember doing this in Math 11? It's a while ago, I know. In the university textbooks, you see it written like this. G, little open circle, F of X. G of F of X. Goth. Okay, flip the page. Now the weird part is, and here's the part that I like, is if this function is continuous and this function is continuous, then the composites are continuous as well. So you don't try and do, if somebody asks you, is h of x continuous? You go, well, I don't know, let me break it into its parts first. Because you can get overwhelmed by looking at a really tough formula. But if you step back and go, okay, I see one function and I see a function inside of that, if I split it into those two and I look at them separately, then it's easy to tell. Because if one part is continuous and the other part is continuous, when you put the parts together, when you make a composite, they're continuous. Flip the page. So that's what I was saying here, is if a function is continuous and g is continuous, then the composite is continuous. Show that this is a continuous function. Okay, look at the graph first. Okay, so I'm going to throw that in my graphing calculator. You don't have to, you can just look at mine. Abs. I don't have any of those. X sine x. Close bracket divided by open bracket. X squared plus 2. Close bracket. Oops. You know it's Friday when? Mr. Epp can't even type stuff in the calculator. 1, 2, 3, 1, 2. Oh, I'm missing a bracket. No? No, I'm good? I didn't close this one here. Yeah, I did. No, I didn't. I closed that one. Oh, Mr. App. Time to go home. Yeah. Okay, graph. Graph. Okay, so Oh, wow. We better make some better window settings there. Yeah, that's pretty good. Don't you? Can't ever see that? Oh. Oh. Where are you? That wasn't the smartest move I've ever made. Okay, we'll try that again. That's a little bit embarrassing. Yeah, anyways, do we agree? Bouncy, 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 bounce. Do we agree that the function is continuous? Yes. As we saw the calculator draw it, it didn't lift its pencil up. Okay. Bouncy, 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 whatever. So is it continuous? Yes, it is. Okay, justify algebraically. There are two functions here. We can call g of x the absolute value of x, and we can call f of x x sine x over x squared plus 2. What? Yes, YEF. Oh. Yeah. Yeah, kind of like I did with the previous example. I just go look for brackets. If I have repetitions of stuff in the brackets, so that's the stuff inside the brackets I call F, and then the stuff outside the brackets I call G. What? Sure. Yes. Yes. Okay. Can you draw y equals absolute value of x? Is there any point of discontinuity on the function y equals absolute value of x? No, because I have not divided by 0 anywhere, you silly rabbit. Continuous? Continuous? Yes. Now, the next one, f of x. Think about what values of x you can substitute into the denominator that will make the value equal 0, denominator equal 0. Oh, root of -2. Everybody, Yes. Good. So there are no values of x. There are no real values of x that cause the denominator to be equal to 0. So is this a continuous function? Yes. So you have to wait until third year mathematics, Math 380 at TRU. You will do the mathematics of calculus of complex numbers. Yeah. No, because it was hard for me. I don't want to embarrass myself. Yes. But if I didn't give you a graphic calculator, let's pretend. This is a good question. Hey folks, here's the pretend question. H of x equals, I don't know, 1 over x plus 2 squared plus 5 1 over x plus 2 to the 7 minus 3 1 over x plus 2 to the power of 4. So your g of x is going to be x squared plus 5x to the 7th minus 3x to the 4th. Your f of x is going to be 1 over x plus 2. So you don't have to talk about h of x, because all you have to say is f is not continuous at x equals negative 2. So this bad boy up here is not continuous at x equals negative 2. Does that make sense? Do you see what I mean? Like, you don't make the big long argument about h of x. You make the quick argument about f, and as soon as you know f is discontinuous, h has to be. Okay? Well, no, it might be a continuous function because x equals negative 2 is not in its domain. But what I'm saying to you is you need to know when you put those composites together that there's a point of discontinuity created at x equals negative 2. That's what I'm trying to get at today. Is you need to know where they are. It's big time important. Okay. Wow. Okay. We're going to try and do this. What? I know, we're going to try. Okay. Page 79. Page 79. Page 79. I'm scared. A function y equals f of x that is continuous on some closed interval a, b takes on every value between f of a and f of b. So, I'm going to draw you a picture. I'm going to start here at a comma f of a. Now I could put that anywhere. And I'm going to go up all the way over to here, b comma f of b. I would like you to join those 2 points up with a continuous function. You can make it as smooth as you want. You can make it as complicated as you want. I don't care, but it must be continuous. Don't lift your pencil. Woo! That was fun. Okay, what the intermediate value theorem says, and this is one of those blatantly obvious moments, but as we move from A to B, as we move from A to B, the function will take on every single value between f of A and f of B. It's one of those right? If you stop and think about it. As we move from A to B, our function will take on every value between f of A and f of B. Now, I know I'm apologizing, but I don't want to talk. We'll talk about example 5 on Monday, but what it's really saying is you're working on a function, and you know that this point is 1 comma negative 5, and you know this point up over here is 3 comma 7. Will this function have an x-intercept? Yes. Why? Well, as the intermediate value theorem says, as you move from A to B, the function's got to go through 0 because it's got to take on every value between f of A and f of B. Every y value. As long as it's continuous. If it's not continuous, it might miss some.